Hey everybody, this is 8.4 log functions. So this might be kind of new, but these are not so bad once you get the pattern. This will be probably just slightly longer than the other sections in this module have been, but not much. All right, so here's the key. If x and b are positive real numbers such that b is not equal to 1, then when we write y, oh, don't have my pen again, y equals log base b, this little subscript right here is read base. B of x is called the logarithmic function with base b. Y equals log base b of x is equivalent to b to the power of y equals x. This is the most important thing in here, okay? Because we have to be able to translate back and forth between exponential form, which is and log form. So on the right, we have exponential form. On the left, we have log form. In the expression y equals log base b of x, y is the logarithm, b is the base, and x is called the argument, okay? B you can always remember is the base when we translate to exponent form. Y is always the exponent, x is the argument, okay? So what we're going to do first is rewrite them in exponential notation. So look at what you have here. I have log base 2 of 32 equals 5. Well, I said base 2, right? So that's going to be the base. The exponent is always what's equal on the other side. That's the y. 2 to the 5th equals 32. This is exponential form, okay? Not so bad. Make sure you know where everything came from. All right, this one says log base 10 of 1 over 1,000 equals -3. So log base 10, it always equals the exponent. 10 to the -3 equals 1 over 1,000. And that's right? Okay, try another. Log base 5 of 1 equals 0. Okay, so log base 5, this is the exponent, 5 to the 0 equals 1. And that we know to be true. Anything to the 0 power equals 1. All right, you try those. I'm not going to do them here. You can work them out. Come into the discussion if you're stuck. All right, now we want to evaluate. So what happens in this case is there is no equals. I have to figure out what the argument is, okay? So essentially, I need to rewrite this in exponential form and see if that helps me first. So I know I'm going to add the x there. I know 8 to the something equals 64. Well, I know what that something is. That something is 2, isn't it? 8 squared equals 64. That's what I have. I'm going to do the same thing here. I'm going to add in my argument, and I'm going to read log base 5 of 1 over 125 equals something. Well, base 5 to some power equals 1 over 125. And then you have to think about how you got from 5 to here, okay? So to turn a 5 into a 125 using an exponent, first I need to flip it, so I know x has to be negative. 5 to what power is 125? Well, 3, right? So if I made 5 to the -3, I would get 1 over 125. All right, this one I'm going to try again. Log base half of 1/8 equals x. Well, I have to think about how I'm going to get there. So I know it's going to be, this is the base, this is x is the exponent. Somehow I have to get to 1/8. Well, if you think about it, how do I turn this 2 into an 8? 2 cubed is 8. So 3 cubed or 1 cubed is just 1. So x has got to be 3, right? All right, you try these. Let's see. For the first one, x should be 3. For number 5, x should be -2. And for number 6, x should be -1. All right, now we have to try some other things. Evaluate the log. Well, I'm going to do this the same way. There's just no numbers. So b to the power of x equals b. Well, if that's the case, I know that the only way to do something to an exponent and get that same thing back is if x equals 1, right? Okay. Log base c of c to the 7th equals I don't know what. Well, let me rewrite that. Let's see what that looks like. Base c to the x equals that whole thing here. c to the 7th. Well, in order for c to something equals c to the 7th, x has got to be 7, right? That only makes sense. All right, let's try this one. Log base 3 of 4, the 4th root of 3 equals x. Well, let's see. I don't want a 4th root in there. I'm going to rewrite this actually with an exponent in it. 3 to the 1/4. Because I don't want a radical in my log statement. So now I'm going to do 3 to the x equals 3 to the 1/4. Well, now I know that x has got to be 1/4 because if 3's are the same, the exponents have to be equal. See, this isn't so terrible. Okay. In this case, x is going to be 1. In the second one, x is going to be 10. And the third one, x is going to be 1/3. Rewrite that radical as an exponent. All right. So a common log is denoted without a base, okay? If you see a log without a base, it is assumed that it's a common log and the base is 10, okay? When the base is not explicitly written, that's your assumption. So instead of writing y equals log base 10 of x, we just write y equals log of x, and the 10 is presumed, okay? So in your calculator, you can calculate common logs. What you can't calculate is anything with a different base, just using the log button on your calculator. So you have a button that says log on it, okay? Use it. You put in the number first and then the log, okay? So the log of, oh, my pages are out of order. Nope. Oh, nope, they're not. Log of 1,000, of 100,000 is when I put it into my calculator is going to be x is 5. I could also just figure it out though if I needed to. So log, I would know this log base 10 of 100,000 is x. 10 to the x gets me 100,000. Yeah. So I'm missing a 0. That's what my problem is. So that's 1, 2, 3, 4, 5 more decimal places. X has got to be 5. All right. This is the same idea. This I can do in my calculator. Okay, that's totally fine. Or I could do log base 10 of 0.01 equals x. 10 to some power gives me, this is really, say it out loud, 1 over 100, 1/100th. So that would be a flip, right? So it's got to be negative, and 10 to the second power is 100. Okay, you should be able to do that in a calculator. You try these. You have a calculator. Please use it, or calculate them using your common sense. We also can evaluate common logs of just things we can't figure out, like me figuring out that this would be log base 10 of 420 equals x. There are limitations to how far I can take this model, right? Because there's no power of 10 that gets me to 420 simply. It would be a decimal number. So you are going to calculate that in your calculator, put in 420, hit log, and you get an approximation. 2.6232 is what you should get. Okay, try this one. So what you would do here is you would do what's in parentheses first, 10 to the 9th times 8.2, and then take the log of that. When you get it, it should be right around 9.1, oops, 9.138. Okay. Try another. The log of 0.0002 gets you negative 3.6990. All right, not so bad. You can try these in your calculator. If you need help, come to the discussion. That's why we're here. All right, this is graphing log functions is a trick. Okay, the thing we have to remember is that logs are inverses of exponents. Okay, so given this, what we're really going to do is find, we're going to rewrite it in exponential form. So we're going to go 2 to the y equals x. We're going to evaluate that. Oh, not 2. Oh, I did that backwards. I'm going to evaluate the inverse. I lied. So 2 to the x equals y. And that's what the inverse of the exponential function would be. So we're going to graph, okay? We're going to find out what this would be. We did this, no, I did it right the first time. At any rate, so if I put in -3, -2, -1, 0, 1, okay? I'm going to get 2 to the -3rd is 1/8, positive 1/8, 1/4, 1/2, 1, 2, okay? And then what I'm going to do is swap out my x's and y's. Okay, so I'm going to put, because they're inverses of each other, I'm going to put 1/8, 1/4, 1/2, 1, 2. Okay, and then I'm going to do -3, -2, -1, 0, 1. That's what I'm going to graph. This is the graph of this. Okay, so what we do is we find the coordinates, basically. If this is my function, if I'm given f of x equals log base b of x, what I find the graph of, to graph what I find coordinates for a different function, for g of x equals b to the x. Then you swap x, y, and y for x. That gets you back to here. Okay, so we can graph this when x is an eighth, y is -3. When x is a fourth, y is -2. When x is a half, y is -1. My dots are too far over here. And then we're here. Okay, so this looks a lot like our exponential function graph. We just turned it sideways. Okay, so when we want to evaluate this one, we're going to rewrite the log as 1/4 to the x equals y. We're going to do the chart for that. Okay, let's see. -2, -1, 0, 1, 2. I'm going to get 16, 8, oh, sorry, 4. I lied. 1, 1/4, 1/16. And then I'm going to swap it. Okay, so I'm going to take x for y and y for x. That's going there. That's going there. So 16, 4, 1, 1/4, 1/16, and then -2, -1, 0, 1, 2. Okay, then I'm going to graph. So I'm still here. Like this, like this, and like this, and like this, like this. Okay, so my graph exponentially that way. You can try a couple, and you should, but here's how this works. Exponential functions and log functions are inverses of each other. So basically when you do that, you take the graphs and you rotate them 90 degrees. These are the exponential functions graphs. These are the log function graph. You can see where they cross at the opposite place, right? The exponential crosses at 0, 1, the log function at 1, 0. Here are the other comparisons. So the domains and ranges are flopped. Exponential functions have a bottom, an asymptote, like a floor they can't go under at y equals 0. Log functions have that at x equals 0 here, okay? They pass, if b is greater than 1, they're increasing, and if b is a fraction, they're both decreasing. All right, the other thing we have to be able to do here is find the domain. So log functions cannot be less than 0. The domain for a log has to be greater than 0. So instead of setting it to 0, what we do is we take whatever is in that parentheses, whatever you're finding the log of, and we set it greater than 0. Okay, 4 minus x has to be greater than 0. So we add x to both sides, or sorry, 4 to both sides. I get -x greater than 4. I subtract. I'm going to go. And then we multiply both sides by -1, right? So we get x less than 4, right? So in this case, the domain is going to be from -infinity to 4. The domain is going to be less than 0, but it's going to give me a positive log, okay? Because I'm subtracting 4 from it. So try this one. So what I'm going to do is going to find 2x plus 6 is greater than 0. Subtract the 6. 2x is less than -6. Divide by 2. Divide by 2. X is greater than -3. X is greater than -3. So we're going from -3 to infinity. That's what's going to make that log work. Okay, you try that one. All right, and now let's try some stuff with it. There's a lot of words here, but it's not a lot of work, actually. There's just a lot of setup. So pH is one of the things that gets calculated using a common log. So the pH of a solution is defined as the pH is the negative log of the hydrogen solution. H plus is the concentration of hydrogen ions in moles per liter. The pH scale, when we find it, goes from 0 to 14. The midpoint is 7. That's something that's neutral. Things below 7 are acidic. Things above 7 are basic or alkaline. Okay, so 1 unit change is a 10-fold change in hydrogen concentration. So rain typically has a pH of 5.6. Some areas in the Northeast, like here, we have more acidic rain. We just have more acidic water all the way around. So what is the pH of a rain sample when the hydrogen concentrations is 0.0002? Well, we use that formula we just saw for pH equals negative log of the hydrogen sample. Well, the negative log, or the concentration of 0.0002 is find the log and then apply the negative, is about 3.7. So our rain is typically much more acidic than other parts of the country. What is the pH of ammonia? Okay, ammonia is much more basic, alkaline. Sorry. If this is the concentration, so what we would do is we would do the negative log of 1.0 times 10 to the negative 11th. You would find 1.0 times 10 to the negative 11th first, then apply the negative log. It's going to be about 11. So the pH of ammonia is really, really alkaline, okay? You can use the formula again to do these, okay? This one, you should be able to get 6.2306. So the pH level of shampoo is pretty neutral. And it should be. It would be strange to wash your hair with something really acidic, wouldn't it? We can also apply log functions to memory. Okay, one of the things that we remember in sort of a logarithmic pattern, So one method of measuring retention of material after you take a class is to retest kids at intervals after the course is completed. The score on the test T months after completing the course is approximated by this formula. Okay, where T is the time in months after they finish the course, and the student score is S of T. So at time is 0, what's the student score? Well, what we do is we put in time of 0, okay? So what we do is we take our formula, equals 85 minus 25 log of 0 plus 1. And then you calculate log of 0 plus 1, log is 1, times 25, 85 minus that. What you're going to find is that their score essentially, when they finished the course, was 85. Okay, so now what's their score? Let's see, after 2 months. So we're going to do 85 minus 25 times the log of 2 plus 1, which is 3. Calculate through. Okay, what you should get is 73.1. So their score is decreasing. You don't remember much calculus. Okay, after a year, remember though that our T is in months. So how many months? So we're going to do 85 minus 25 log 12 months plus 1. That's what you're going to calculate in your calculator. You're going to get somewhere in the neighborhood of 57.2. Their score went down quite a bit, right? All right, so this is how log functions work. You should be able to do this. Try it out. If you need help, you know where to go. I'll see you in the next section.